Hi, my name is Javier Flores, and for this assignment, we're going to be looking at various spectral analysis tools of a compound to see if we can determine its structure. The structure in question is a 7-carbon, 14 hydrogen, 2 oxygen molecule. And so to start off, we'll be looking at this first piece of this puzzle, as I like to think of it, which is this IR spectrum. The first peak that we see is this first functional group that appears to be at the 2900 marker. We know that this molecule will particularly have an sp3 carbon-hydrogen bond. The next functional group is this group right around here at the 1740 range, and this sharp end is usually associated with a carbon double bonded to an oxygen. The next functional group is roughly here around the 1190 range, and here we would see a carbon single bonded to an oxygen. So based off of the data, we can deduce the presence of an ester, considering that we have an alkane groups, a carbon double bonded to an oxygen, and a carbon single bonded to an oxygen, which I went ahead and rough sketched that ester over to the right based off the data. So next we'll look at this 13 carbon NMR spectral analysis, which recognizes distinct carbon environments in compounds. It's also worthy of noting 2 or more compounds that have the same environment can be represented by a single line, which we will see here eventually at the 22 marker. So as we scroll down real quick, we'll talk about the degree of unsaturation given the formula of the molecule that we have. We can plug those numbers into this formula here, where it will be 2 times the number of carbons in our molecule, which is 7, plus 2 minus the number of hydrogens in our molecule, which is 14, divided by 2, and we can see that the mass shakes out to be 1 degree of unsaturation, indicating the presence of a double bond, which is typical for an ester, further only confirming our suspicion. So referring back to the 13 carbon NMR, the first spike that we will see was at the 172 marker. We know that this has a carbon that is attached to more electronegative atoms, such as an oxygen, and they would appear more downfield over to the left and would thus be at about the 180 to 170 marker, which is what we see right there. So as we scroll down very briefly, here labeled as carbons 1 through 6 only indicates how much further removed they are from the electronegative atoms. So here we have carbon 1, 2, 3, 4, 5, and 6, and I have those labeled over here onto the table as well. And so as you can tell from the chemical shift is more upfield the further they are away from that oxygen. So carbon 1, or this particular methyl group over to the right, will be at about 14. Carbon 2, this CH2 group, will be at around 60 or 61. Carbon 3 is that carbon double bonded to an oxygen that we talked about, or that first peak, which is at about 172. Carbon 4 is at about, or the CH2 group is at about 44. Carbon 5 is at about 25. At the 25 peak, and carbon 6s, or those 2 methyl groups that we see here at the end to the far left, would be at about the 22 marker up here in this table. And as we mentioned previously, the 2 or more compounds that have the same environment can be represented by the single line. So next we'll look at the HNMR, and I'll go and scroll up to this data here and use these as my reference point. And so here we see about 5 different spectrum spikes, which are labeled under the multiplicity column that we see down here in this table. So the first spike that we see here is at the 4 marker, and we have a quartet. The next one will be at the 2.4 marker, which is a doublet. The one following that to the right of that will be at the 2.2, which is a septet. And then these last 2 over here to the right will be at the 1.1, which is a triplet, and a 0.9. And so, as mentioned, the first spike that we'll see is at the 4 parts per million. And there are about 4 spikes. And so this has a 2H integration, which is the amount of hydrogens that are connected to the carbon. And so we can see it further downstream, which leads me to believe that it's closer to the oxygen. So because of the data provided, we know that we have a presence of the ester already. So we know that this oxygen will connect to another carbon, which will connect to another carbon. And so here we have our proposed structure, if we scroll down, as well as our interpretation. So we have a CH2 group here, where we have the carbon 2 in our rough sketch. And we have a CH3, and so this oxygen is connected to this carbon, which is connected to another carbon, along with the presence of an ester group. So now as we move down the list, we'll look at the peak at 2.4, and so we'll be looking at this carbon here, carbon 4. We have 2 hydrogens connected to it, to this carbon, and so we can see it further upstream because it's not directly on the oxygen, since one carbon doesn't have any hydrogens. And so the carbon that we are talking about, which does not contain any hydrogens, is this carbon here, carbon 3 in this rough sketch. And so we have the CH2 group at carbon 4 connected to carbon 3 and carbon 5 here. And so next, we'll look at the 2.2 peak, which is this carbon here, carbon 5, and we have a 1H integration since this carbon carries only one hydrogen and is connected to these 2 methyl groups. And so the one after that we have at 1.1, or carbon 1, and we have the 3H integration since this carbon here, or this methyl group over to the right, will carry the 3 hydrogens. And last but not least, at the 0.9 peak, we know that we will have that this particular peak will be the one that has the least electronegativity, which means it's the carbon that's furthest away from the oxygen. And so here at carbon 5, we with this carbon connected to 2 other carbons, we have 6 neighboring hydrogens, which will give us this 6H integration. So therefore, with the data provided, I believe the correct proposed structure based off of the data, we will have a ethyl 3-methyl butanoate, which is the correct structure for this analysis. Thank you.